Hello everyone, my name is Arpita Gaikar and today I am going to talk about the principles of the light microscopy. When we look at the world around us, our eyes can only see objects up to a certain limit. But what about cells, bacteria, or a microscopic life forms? To explore this hidden world, scientists use light microscopy. In this video, we will explore the principles behind light microscopy and understand how simple light and lenses allows us to see the visible. Light microscopy is a technique that uses visible light and optical lenses to magnify biological specimens. It is most widely used microscope in educational, clinical, and the research laboratories. Despite the development of advanced microscopes, light microscopy remains essential because it is simple, cost-effective, and reliable. It allows magnification up to 1000x, which is sufficient to observe cells, tissues, and many microorganisms. The evolution of the light microscope is closely connected to the history of biology. In 1665, Robert Hooke observed cork and the discovered cells. After 9 years, Antony van Leeuwenhoek later observed bacteria and the protozoa, becoming the first microbiologist. Ernst Abbe and the Kohler later improved lens design and the illumination. Each advancement increased accuracy, clarity, and the scientific reliability. The scientific foundation of light microscopy was given by Ernst Abbe in 1873. He explained that the image quality depends not only on the magnification but also on the wavelength of light and the numerical aperture of the lens. This led to the concept of the resolving power, which defines how clearly two closely spaced objects can be distinguished. Magnification is the process by which a light microscope makes very small objects appear larger. It is achieved using two lenses, the objective lens and the eyepiece lens. The objective lens forms a real inverted image of the specimen and the eyepiece further enlarges it into a virtual image that we see. Total magnification is calculated as objective lens into eyepiece lens. However, magnification alone is not enough. Good resolution is necessary for a clear image. Refraction is the bending of a light when it passes from one medium to another, such as from air to glass. In light microscope, this bending by curved glass lens helps to focus light and form a clear image. The amount of the refraction depends on the refractive index of the materials used. Air gaps reduce image clarity, so immersion oil is used to improve brightness and the resolution. Resolution is the ability of a microscope to distinguish two very closely placed points as separated. It is the most important factor affecting image clarity. High resolution allows finer details to be seen clearly. Increasing magnification without improving resolution results in an unclear image, known as empty magnification. Proper illumination and the high numerical aperture help improve resolution. Numerical aperture or NA measures the ability of a microscope lens to collect light and resolve fine details. It depends on the refractive index of the medium and the angle at which light enters the lens. A higher numerical aperture allows more light to enter the lens, producing a brighter and sharper image. Therefore, numerical aperture plays a key role in improving resolution in light microscopy. Most biological specimens are nearly transparent, making them difficult to observe. Contrast creates visible differences between structures by altering how light interacts with the specimen. Staining and the special optical techniques increase contrast without damaging the specimens. Image formation in the light microscopes occurs in stages. First, light from the specimens enters the objective lens, forming a real inverted image. This image is then magnified by the eyepiece into a virtual image visible to the observer. Proper alignment of the optical components is essential for the accurate image formation. Working distance is the space between the objective lens and the specimen. Higher magnification lenses require shorter working distances. While the improved resolution, it increases the risk of damaging slides or lenses. Careful focusing is therefore essential during microscopy. Thank you for your attention. I hope this presentation has provided a clear understanding of the principles of the light microscopy.